The name is New Inverse Problem Approach to Thin Soil Layer Identification, Application in Earthwork Engineering, and Eileen Martin from Virginia Tech will give the talk.
Thanks very much. I'm glad to see you all today. And yeah, I'll be talking about basically a new area where there haven't been inverse problems used very much in the past, but where we're trying to introduce those. And so going through that process of how do we actually even design an inverse problem that's a good fit for this application. A lot of this work was with John Cooper, who's a master's student who recently graduated, as well as Kaylee Yost, who's a PhD student here, my colleagues Alba Yarrow and Russell Green, who are both faculty in civil engineering. So the motivation for this is really looking at a problem that's called earthquake liquefaction hazards. So that's where when there's a large earthquake, if you have soils, especially maybe sandy soils that might be saturated, as the earthquake shaking starts, if it's really quite strong, it can actually cause those soils to basically fail and fall apart, act like they're a liquid. So this means sometimes it shows up with basically these sand boils that kind of show up at the surface, and it's especially dangerous if you're having any kind of infrastructure or structures built on top of this. So one of the locations where this has been a major issue is Christchurch, New Zealand, and so that's part of the data that we're now analyzing with the methods that we've developed. So in this space of sort of geotechnical engineering, near surface geophysics, there has been some application of inverse problems in the past, but typically it's over on this side of looking at seismic imaging, where we send mechanical waves through the ground. We have an array of sensors we're trying to detect when certain vibrations are hitting which parts of the sensors to infer maybe the speed of sound or the speed of those seismic waves underground. So that's the space where I'm usually in my kind of sweet spot comfort zone, doing either active source seismic or using just random seismic noises, basically PDEs with random right-hand sides to then infer what our wave equation Green's functions are. But in this problem, we're working on this technology called cone penetration testing. And when I'm working in the seismic realm, I look at cone penetration testing and I think that's my ground truth. So with cone penetration testing, you're pushing a sensor down into the ground and you're seeing basically how much resistance is there at every depth to your probe that's going down. So you're kind of inferring how stiff is the soil, how strong is it? But really, this is not even our true ground truth, as you'll see in the next few slides. So what's our true ground truth is really having soil core samples where we really have drilled in and pulled out samples of the soil. And okay, these soil core samples are nice because it's a very direct, reliable measurement, but it's pretty expensive to do. It's much faster and cheaper to do these kind of cone penetration testing. Also, we typically are expecting that we're not going to put a lot of compute power towards these kinds of analyses since we treat them more like direct measurements. So that's actually one of our limitations that you'll see. Over here on the right-hand side, we've got a lot more compute power that we're willing to throw at these problems in seismic imaging. Okay, so with cone penetration testing, just getting a little more specific about what we're measuring, we take a cone penetrometer and we're going to push it into the soil at a constant rate. It's going to go maybe 10 meters into the soil typically, or if we're doing sort of laboratory testing, it might just go 1 or 2 meters into the soil. And at every 2 centimeters, we're going to record what is the friction of this little sleeve that's down at the end of our cone penetrometer, and then also what's the resistance at the cone tips. We've got a little electrode down there that's measuring that. And so we get a depth profile, and we really care mostly about our tip resistance more than our friction. So we're just only going to worry about these tip resistances, which I also denote as QC here. So we're actually able to model this process, but it's not totally straightforward on how we do this modeling. So the method that my colleague Alba Yarrow specializes in is called material point method. So this is a PDE forward simulation method where you actually maintain both a grid and actual material points. So when you have things like soil failure happening, where you have many grains of your material that are kind of getting pushed around, or where you have a mix of liquids and solids, and those are getting pushed around, this tends to work a lot better than some other methods. So you don't have to worry about like mesh tangling and those kinds of issues. And so over on the right, you can see one of the meshes that we've used for material point method simulations. So Kaylee Ghost, who's a grad student, has put this simulation together. And you can see if you had maybe a couple of layers of interbedded soils of different types, one that's more like clay, one that's more like sand, we're actually, as our cone penetrometer goes down, we're actually dragging down some of that soil. And that's actually part of what blurs our measurements when we're recording cone penetrometer data. And you can even see in laboratory testing, when you've got these alternating thin interbedded layers of soils and sands, that we're getting that drag down of the materials. And so that process makes it a lot harder to kind of model what's going on. We can see also that as our cone penetrometer goes down into the soil, if we were to measure what's our strain at every point, we actually get this bulb of like strain and stress that happens around the material. And so that means that even the materials that aren't directly touching our cone penetrometer are affecting what our measurement is. It's basically blurring it out. And this has been modeled in the past with just very simple kind of setups. Maybe you have two layers with maybe a softer layer above a stiff layer or a stiff layer above a soft layer. And people have proposed various just simple analytical expressions to try and correct their cone penetrometer data, basically pull out this blurring that happens and pick out where is that sharp interface between the soils. Because when we're working with soils, we oftentimes have these kind of sharp interfaces between them. This issue gets a little bit worse though when you have multiple layers. So let's say if I have a soft, then a stiff, then a soft layer, I'm going to start to have my measured tip resistance. And I'm going to have that blurring both on the top and on the bottom of my layer, making that layer's width harder to pick out. And especially if I'm in a case where I've got maybe a stiff, then a soft, then a stiff layer, I'm trying to pick out that soft layer because that's the layer that might actually put me at greatest risk for earthquake liquefaction hazards. So being able to pick out these very thin layers of soft materials is really important for our geotechnical engineers. You can imagine that if this layer got even thinner, you would actually just have this blurred portion that you're looking at, and you would never get all the way down to this lower value of what you would expect your tip resistance to be if you were just in a uniform soft material. So you might never actually even estimate just how soft your material really is in that layer. So you might miss some earthquake liquefaction risk. So if we have multiple layers, this means that we're starting to get these blurring effects, one right after the other. And if our layers are thin, which happens in some scenarios, that means that we've got these compounding thin layer effects that can really blur out what our data look like. So over here on the right, I've got a profile marked in white and gray of where we've got two different soil layers, just a soft and a stronger one. The stronger layer is marked in gray, is marked in white, and the softer layer is marked in gray. And if we were to just do just a uniform profile measurement for each one of these, which we're going to say is our true profile that we want to be able to recover, that's going to be this blue line here. But our actual measured data from the laboratory is shown in black here. And you can see that it pretty much just stays around this softer value, and it just sort of alternates and wiggles. And we've been able to do forward modeling with material point method to kind of model that and at least somewhat approximate it. There are still some slight differences. But this means that we're getting really far away from what our true profile looks like when we're looking at that real data. So we want to be able to de-blur it. So Boulanger and de Jong a few years ago actually proposed an inverse problem approach for this problem for the first time. So they were just going for a simple sort of de-blurring model, just looking at what's the misfit between a simple convolutional filter or point spread function convolved with their depth profile that they're guessing, and then what's the difference between that and their measured data. So you've got your measured data profile, you have some guess at your true resistance profile here in blue, and then you're going to computationally blur that. In Boulanger and de Jong, it's just a simple convolution with a filter that they sort of experimentally just tried to match from a limited set of laboratory data. And then you look at what's your misfit between your simulated or your artificially blurred and your true measured data, and then update. And in their case, they just did a simple iterative splitting scheme and then just a gradient descent type update. So now we can actually see this, that we go through this whole process of updating what is our profile until eventually we get some corrected profile. So in principle, we follow the same scheme, but we found that this hasn't always worked great in practice. One other thing, when you're thinking about why are they using this simple blurring? Well, when we think about the material point modeling method, we have this issue of what are our expectations for the applications engineers. So with geotechnical engineers who've been working with cone penetrometer data, they're typically used to things that just get analyzed right away on their laptop within seconds at most. They're not used to waiting for an HPC simulation to happen. With these material point method simulations, these profiles that were simulated typically take several hours at a time. And so when you think about integrating that into your inverse problems approach, if you're doing that for a community that's not used to that kind of turnaround time, you have to think about what are other ways we can do simple surrogates. Another issue is that actually with the material point method forward modeling and any other forward modeling of these soil failure processes as we have our cone penetrometer moving through the soil, we actually don't have there are still a lot of open questions on how generalizable the different models are. So we made a lot of assumptions to do these kinds of simulations to match laboratory data. Things like if it's drained or undrained, what's our friction or dilatancy angles, whether we can do axisymmetric setups in the field, that's a big open question. And so these kinds of things that we do, it's not clear even in the forward model how we do a good simulation. So is it worthwhile to do these very expensive simulations when we're still not even sure how generalizable they are across different soil profiles and conditions? There's also an issue that our open source software for doing this kind of simulation doesn't have an automated geometry and meshing integrated into it. And so that makes our updates to what our soil profiles are really hard to do as part of an inverse problems workflow. I think that this is a problem that can be tackled pretty easily through some software engineering in the future. So, okay, we can't quite use the material point method limitations, or we can't quite use the material point method for our simulations in our inverse problem, but at least we can start to evaluate at least other blurring procedures to get a baseline for where we want to go. So Kaylee, who's a graduate student in civil engineering, went through and actually looked at a bunch of data from Christchurch, New Zealand to evaluate with these different kinds of inversion procedures, including the Boulanger and de Jong procedure, as well as one that she's modified to have some additional smoothing steps throughout it to see if she could get it to perform better. We were looking at what's the area under the curve of false positives and true positives. And typically we found that the best corrected version of our profiles actually did a worse job at predicting what our soil liquefaction should be in this Christchurch, New Zealand data set where liquefaction was an issue than just leaving the data uncorrected altogether. So in the best case scenarios, sometimes we would also get maybe about 1% or maybe 1 to 2%, never a really good improvement in our actual end outcome, which is what is our area under the curve of predicting soil liquefaction from a data set that's been corrected. So these were pretty limited. We saw that there's a lot of open room to improve our inversion procedure. So looking at that Boulanger and de Jong inverse problems procedure, in principle, it's a great idea, right? We just want to use a simple iterative splitting scheme to update what our profile is, and we want to be able to kind of have some kind of simple blur function that's going to match our data. But in some cases, we're really falling into our local minima, and we're actually getting a solution which is not physically realistic. So over here on the left is just a simple laboratory test of basically 7 layers of material, just alternating 2 different materials. And the data that was measured is shown in this black line here. And after applying that simple optimization procedure, we get this profile in red that's supposed to be our corrected one. And we can see that this is not physically realistic. It's not telling us what we know was set up for this laboratory test. So clearly there are some issues with just the simplest setup of this inverse problem. We tried applying smoothing at each iteration, tried different global optimization techniques while still maintaining the same objective function. We've also added some total variation regularization and tried that. So I'll show you those results in a minute. But we still ended up with issues. So it seemed like a natural fit for us to try just deblurring with an L1 term. Basically, take your derivative of your soil profile, which is marked as N here, and just add that as an extra term. You want to just have a limited number of points where you're changing your soil layers, so a limited number of points where you want to have that high derivative. And of course, this is a really common process for deblurring images. Okay, so we tried this out. We tried this both with blind deconvolution and unblurred because we wanted to know, is the point spread function that was provided to us by earlier papers from experimental results, is that even a good point spread function? And we found that really, if we tried to find our optimal point spread function for describing these data from some simple synthetic tests and laboratory tests, we found that actually the point spread function that had been provided for us previously by engineers was not the greatest fit. We did come up with a simple expression that was just based on basically a truncated chi-squared distribution that tended to fit the data a little bit better. But we don't have a good physical intuition for what our blurring function should be and how we interpret that physically, as far as in terms of the stress bulb and the soil displacement yet. So that's still an open question. We tried a variety of different methods for doing this kind of optimization with that sort of total variation type term added at the end. So we've got our original data here in blue, our actual results from a primal dual method, doing Bregman without having a blind filter, doing Bregman with just blind deblurring, and then another variation of a split Bregman method here. And none of them were really giving us profiles that matched the profile that we knew we needed to go for, which was this red dashed one. So we saw there were still limitations even in doing that kind of deblurring with our total variation term added in. But we got some inspiration from seismic surface wave imaging, which our geotech engineer friends were much more comfortable with. It's because it's a tool that they're already used to having in their field. So just thinking about this cone penetration problem or CPT test problem, we're trying to go for these layered models, right? And when people are working with a technique called SASW or MASW, these are both surface wave inversion methods. They're always going for inverse problems where they have a set number of layers for the soil properties that they're going for. And then they just try to adjust what's their seismic velocity in each layer and what's their thickness of each layer. So we decided we're going to go into basically the same model space. We want to say, what is the tip resistance of each layer if it were measured as a uniform profile? And then what's the thickness of each layer? So we've got a new inverse problem, but it still fits basically the same workflow as what Boulanger and de Jong were doing. As far as, updating the same thing, all of that. So now, instead of having a model M, which has a value for the tip resistance at every single point in space that's every 2 centimeters in our depth profile, now we just want to have N layers. So we keep track of N variables that say what's our thickness, and then N variables that keep track of what is our tip resistance if they were uniform layers. So we want to be able to get that corrected tip resistance there. So then we're just going and doing this optimization problem over the space of just 2n dimensional vectors. So this brings us down into a lower dimensional space. That's helpful for us. And it also helps us just keep our problem a little bit more tractable for engineers who want to be able to run this in the field very rapidly. Okay, so we had to change the optimization procedure just a little bit. We had to come up with new processes to improve our automated initial guesses. We also had to add algorithms to add or remove layers. That was not part of what was previously in the Boulanger and de Jong setup. And then we also started using particle swarm optimization just as a global optimization method instead of gradient descent. We found that that tended to work better for our problem. So overall, here's our algorithm. And so just going through the blocks, big picture of what's here, we're basically setting up our initial model where we're basing that off of where are we getting changes in curvature in our measured data, because it tends to be that kind of blurry back and forth, but those S's or curves, they kind of tell us where we've roughly got layers as sort of a starting guess. So we had to come up with algorithms for that. And then we would do just a little bit of coordinate descent to see if we could sort of adjust what our tip resistances were just slightly, if there was any little changes we could make there. And then we go into checking, how do we actually know that we have the right number of layers? So first, we're going to go through a process to leave a layer out. And so we leave a layer out if that's going to help. We go into this algorithm to do that. Then we're just going to do a little bit of particle swarm optimization. Then we're going to see, do we need to add any layers in other portions of the profile? Hopefully you're not leaving a layer out, then adding it back in. If that happens, that's actually part of the checks that we do as we go through this. Once we're sure that at this point we're at a reasonable number of layers for our current guess, then we're going to go and actually just check again, make sure we get our last layers. And then we have to check for if there are any kind of warnings of unusual behavior that happened during this process. But once we've gone through this procedure many times, eventually we get to a much better model. Okay, so just to give you a feel for how we're actually checking if we have the right number of layers. With our leave one out algorithm, we basically have our current inverse model, which is here in red. That's like our current guess. In the red dash, we have what is our blurred version of our model using just a simple synthetic blurring function that we have. And then we have here in blue, I've just marked what is our observed tip resistance from our measured data. And we need to decide, do we want to actually leave out any layers from what we currently have? And you see that there's this huge misfit between our blurred guess, which is in red, that's like our synthetic data, and our true data in blue here. And so what this algorithm does is it just goes one layer at a time. It's checking what are these misfits if I were to remove the layer and set it to just the previous layer above it to have the same tip resistance there and just kind of extend that. And so then we see that, okay, we should drop this bottom layer and then we get a much better misfit afterwards. So it's a relatively simple algorithm, and there's a similar algorithm for adding one in as well. But these were issues of adding and removing layers that we found we needed to be very sensitive to making sure that that was possible at each step as we update our tip resistances. Okay, so just looking at a sort of simple synthetic test, we've got here on the left our initial guess shown in red, solid line here, on top of our true tip resistance, that's what we really want to go for in blue, solid line here. And then we've got the blurred versions of our initial guess and our true profile, or our observed profile in the dashed lines. So you can see they're mostly the same, but there's like a little bit of offset. And afterwards, we got pretty good results of, at least on this very simple test, getting our final model to really match what our true profile should be. And this problem, it's relatively simple. It was just kind of a make sure that it works thing. But I will say that even some relatively large changes in the profile can still lead to quite small changes in your blurred profile or your blurred data that's observed. And so for us, this is actually like a pretty good success. There are still some limitations. So over here on the left, you see some examples where we get sort of some different results where suddenly there might be a very thin layer or an unnecessary layer. And so we have all of these thresholding parameters you have to choose on how sensitive are you to adding extra layers or dropping layers. And so this is something where I think that we still have some work to do on automating our ability to make sure that we have the right parameters set for how sensitive we should be to adding and removing layers. And if there's a bunch of thin layers, we found that sometimes we would just miss whole chunks of those thin layers. Their profile that's measured is just blurred together a little bit too much for us to see easily there. And the other thing is that we tend to just focus on kind of very large scale misfits. So when we really zoom in afterwards, we see that we're missing, like in our resulting profile here in red, we're missing like 4 layers in blue that we should be recovering, even though our profile looks like it's a pretty good fit when we're zoomed out. When we zoom in on that blur, we see these very fine details. So we found that we really needed to rescale the problem a bit. So we ended up coming up with a new objective function here on the right that we're just looking at the logarithm of this. And so it's basically calculating as we go through each of our different points, we look at the logarithm of those differences instead of the actual data themselves. And so that just lets us have kind of a much narrower space where we're going to be zooming in towards our optimal solution. And so after we make that change, over on the left here, I've just got our starting guess that we came up with, which is basically the equivalent of what an engineer would do if they just had to come up with a simple automated script to correct their profiles. In the middle here in red, you see if we just used our standard misfit function for the objective, we're missing a few of these layers down here. And when we use the log misfit, we get every layer almost perfectly. There's one down here where we've got a little bit of a tip resistance offset, but generally getting a much better result by doing this rescaling of the problem. So up at the top, there are still some unusual features as far as capturing those gradients that we're trying to work on. So here, we're pretty good in all of these layers, much bigger improvement down here and better down at the bottom. So we've released open source code here on GitHub for this optimization procedure if you want to test it out or build on it, adjust it. And we've got some steps going on right now where we're applying these procedures to actual data in Christchurch, New Zealand, to compare to all of the other previous procedures that we've seen have some limitations. Over on the right, you see a map of where there was liquefaction that happened during the Christchurch, New Zealand earthquake about a decade ago. And we're also trying to find improved physically realistic models of our simulation for our forward model that are maybe better than our convolution that we're using right now, but maybe not so expensive as our NPM simulation. So trying to find some kind of improvement there. So just to acknowledge our funding source, this was funded by National Science Foundation, thanks to Virginia Tech, Advanced Research Computing, and all of our collaborators. We have a few references out. Some of these are under review and one has already been accepted. So I'd encourage you to take a look at those and take a look at the code. Thank you.
Thank you very much, Eileen. We have time for questions or comments.
I have a question. Just to clarify, because you still doing the deblurring so this step where you try to adjust the number of layers, are you still doing the deblurring process or is it a completely new algorithm? I missed that part. I don't know if it's clear, my question. Or...
That's a great question. So I would say that it's not doing deblurring in the sense of doing a gradient update when you're adding and removing those layers, but it is still trying to find a model that's forced to be a layered model. So it's more about changing what is that model space that we're doing our inverse problem in the first place, more than changing like what the blurring function is or anything like that. I'm not sure if I totally hit the answer.
Mm-hmm. No, yes. Mm-hmm. No, because I was I'm working in a method looking at actually the deblur. If you don't know, but you have some idea of how the blur should be, but then the parameters, so it's more like a blind deconvolution with some particular blurs, but then the optimization is kind of the one that you put there, I guess, the blind Bregman, but yeah. I wonder how it will go, but you have data, so we can play with it.
Yeah, definitely.
You have more questions or comments for Eileen? Well, we thank you, Eileen, again. And we have the next work. Diana Rubio is the author. Well, again, the next talk will be given by Helcio Orlande from the Federal University of Rio de Janeiro, and the title is Characterization of Pipelines During Flow Transients. Thank you, Professor Orlande.
Thank you. Thank you. Can you see my screen?
Yes, okay, it's okay.
Oh, okay. All right. Okay. So good afternoon. Thank you very much. It's a pleasure to be here. This work was the master thesis of the first author, Rafael Carvalho. It also counted with the collaboration with two friends, Marcelo Colasso from my department, and Italo Madeira, who is with Petrobras, that is the Brazilian oil company. So this is the outline of my presentation. I'm going to present a brief introduction on the motivation for this work, the mathematical formulation, the solution of the direct problem, the solution of the inverse problem, some results and the conclusions. So the motivation for this work is to estimate parameters of what is called a water hammer model. And water hammer is a phenomenon that takes place in transient flows. Actually, when there are very fast transients imposed, for example, by a valve being closed or some pump being turned off. And because of those fast transients, there might be some pressure waves of large magnitudes that can even cause plastic deformation in the pipelines, like it is shown in these two figures here. The mathematical formulation for this problem is taking the form of a system of two equations, and the problem is considered one-dimensional, but x is the coordinate along the pipe. So actually, the pipe can change direction, can change to a higher elevation, whatever. Here, u is the vector of state variables, which is given by the pressure P and the mass flow rate Q. The density can vary because of the large pressure oscillations, and same thing with the area of this pipe. Okay, it may change in size. The source term for the momentum equation, which is given by this term here, it includes the friction factor. It includes also a term that is due to the change in the elevations, the pressure, the variation in the area caused by the pressure, localized pressure losses, for example, like in valves or in T's, in E's, and a term that is a friction term that is results from the transient flow. Okay, because this friction term, it's usually associated with the fully developed flows. So it does not really take into account the transients. So this term here accounts for the transient friction, and it involves this this parameter here, Fu, which is the transient friction factor. The model also involves A, which is the sound velocity. It's also called the celerity. Oops, I'm sorry, the celerity, and which includes a parameter that psi that is related to the elastic properties of the pipe and also of how this pipe is supported when it's constructed. For example, for a rigid pipe, this value can be 0. And there are some expressions in the literature for example, for a thick wall or for a thin wall elastic pipe with expansion joints like this. This system is hyperbolic. Both eigenvalues of the Jacobian matrix, they are real and they are distinct. For its solution, we use a split scheme that the non-homogeneous partial differential system, it's split into a homogeneous partial differential system and an ordinary differential equation system that is non-homogeneous. And so this for each delta t, for each timing increment, this system, this homogeneous system is integrated first, and by using as initial condition the value of the state vector at the previous time. And the result of this integration gives the initial condition for the integration of the ODE system. For the integration of the partial differential system, the homogeneous partial differential system, we use finite control volumes, an explicit scheme of finite control volumes given by this expression, and the fluxes at the surfaces of the control volumes, they are obtained by using what is called this weighted average flux total variation diminishing scheme. So we have this expression, but this is pretty much a standard method and can be found in text reports. For the solution of the inverse problem, we solve the inverse problem within the Bayesian framework of statistics by making inference on the posterior probability density, which is the conditional probability of the parameters p given the measurements y. So from Bayes' theorem, the posterior probability density can be obtained from the prior density, which is the information about the parameters before the measurements are taken, coded in the form of a statistical model, and also of the likelihood, which is the condition of probability of the measurements given the parameters, which is obtained from the model for the measurement area. This density in the denominator, it's called the evidence. It's normalizing constant, and usually it's not required to be known. So for the inference on the posterior distribution, it's actually made from by stochastic simulation, by applying a Monte Carlo, a Markov chain Monte Carlo method. So we generate samples of the posterior distribution over this Markov chain, and which is represented here, for example, for one single parameter. And we hope that this chain reach equilibrium. And after it reaches equilibrium, we can use the samples to make inference on the posterior density. And this is the representation that what happens, for example, when we have two parameters. Okay. So all those states, they are called the burn-in states, and they are the states that of the distribution when the Markov chains have not reached an equilibrium distribution. So as any Markov, as any Monte Carlo method, it's very time consuming, and so especially for this case that we have to solve that system of equations for the flow in the pipe that may be a very long pipe, and so this solution of the direct problem is actually very time consuming. So in this work, we have used the recent parallel version of the Metropolis-Hastings algorithm from this reference by Cui, Fox, Nichols, and Sullivan, and trying to reduce the computational time for the solution of the inverse problem. This is the vector of the model parameters, and there are actually two groups of parameters here. This one, which has the diameter and the thickness of the and the Young's modulus for the pipe. K, which is the compressibility modulus for the fluid, and rho 0, which is the is a reference density for the fluid. These are fairly well known, and so we have used priors given by truncated Gaussian distributions in this case. However, these two parameters, that the transient friction factor and that elasticity parameter that is related to the pipe and how the pipe was constructed, it depends a lot on this construction characteristics and also on the fluid and the flow conditions. So these are the two parameters that are most uncertain before the measurements are taken. And so this our objective is actually to characterize the pipe and the flow in terms of these two parameters during a water hammer phenomenon. Okay, so for these two parameters, we have simply used the uniform priors with bounds given by positivity constraint and also from the expressions available in the literature for the delta. Besides that, the measurement errors, they were assumed as additive, Gaussian with zero mean, uncorrelated, and with non-variances. Now for the results, we have this, we have constructed a hydraulic circuit in our laboratory. Here we have the water tank and a pump and all the pipes, they go around over the wall of the laboratory. So we have a total length of 150 meters. Although the circuit has already been tested in terms of leakage, the instrumentation has not yet been connected to the data acquisition system because of the pandemic. So the results that I'm going to present to you, they are based on simulated measurements. Simulated measurements that were taken by flow rate and also pressure instruments at the inlet and at the outlet of the circuit. The simulated measurements, they were taken with those reference parameters, where here the transient in the flow is induced by the closure of a valve at the outlet of the pipe, and after a steady state is what was reached. So we reach a steady state, and then 4.1 seconds after the steady state was reached, we close this valve, and the closure of this valve takes 5 seconds. So we have these simulated measurements at the inlet of the circuit at the position of 4.59 meters, and these simulated measurements at the outlet of the circuit at the position of 148 meters. So we can see here at those figures for the flow rate, the closure of the valve when the flow rate becomes 0 after 5 seconds here, that the valve was closed. And because of the closure of the valve, we have an increase in the pressure that eventually reaches the pressure imposed by the pump. But we have those oscillations that, especially in the sensor that is closer to the valve, is near the valve, and these oscillations, they are dampened towards the inlet of the pipeline of the pipe, as we can see from the simulated measurements from the inlet sensor. These measurements, they were simulated by adding Gaussian errors with a standard deviation of 500 Pascal for the pressure and 0.08 cubic meter per hour for the flow rate. We examined the reduced sensitivity coefficients of the measurements at the inlet and at the outlet of pressure and flow rate with respect to the parameter psi and with respect to the parameter FU. And they are completely different. They have different behaviors, so the parameters are not linearly dependent. So the parameters are linearly independent, these two parameters. And for the implementation of the estimation procedure with the simulated measurements, we examined 6 cases. For the first 2 cases involved the serial Metropolis-Hastings algorithm, while the other 4 cases involve that parallel version of the Metropolis-Hastings algorithm with 3, 7, and 10 cores. These 2 cases 1 and case 2, they differ by the way that the candidates were generated in the Metropolis-Hastings algorithm. For the first case, we have used a constant, a Gaussian random walk process with a constant standard deviation. But for the second one, after 1,000 iterations or 1,000 states of the Markov chain, we have reduced this standard deviation of the proposed distribution. Same thing here for when we compare case 6 with case 7. Okay? The computational time for cases 1 and 2 with the serial algorithm were very large. Okay? So we have run only 4,000 states in the Markov chains. The number of accepted states were about 10% of those states. For the parallel version of the Metropolis-Hastings algorithm, the speed factors were quite good. Actually, they have even reached 4.71 here for this last case. And we were able to run 8,000 states. However, the number of accepted states dropped. While here in the serial version we had about 10% of accepted states. Now we have about 5% of accepted states. Okay. So these are the results for the serial. Okay, I'm here. Those 2 cases that are highlighted are the ones that I'm going to present the results. Okay. So for case 2, these are the results. So with the serial algorithm, we can see that the states in the samples of the Markov chains for FU and psi, they eventually reach the reference value that was used to generate the simulated measurements. But after these values are reached, we can see that the number of accepted states, the acceptance rate of the Metropolis-Hastings algorithm, it drops a lot. Okay, and we see in this figure that the behavior of the posterior distribution, and it actually reaches a very small value as the Markov chains evolve. Similar results were obtained with the parallel version of the Metropolis-Hastings algorithm here, and basically the same behavior. After the parameters of the samples of the parameters, after they reach the reference values, actually the acceptance rate decreases a lot, and it's almost 0. So what we believe here is that the likelihood is actually so sharp, so peaky that when the samples get into that region of very large likelihoods, they can never get out. Okay, so it's but we are still investigating what is happening here. So as we expected, when we compare the means at different regions of the Markov chains, the means are very close. Okay, of the samples. These are the means of the samples at the different regions of the Markov chains. And the standard deviations, they are very small because the acceptance rates drop a lot when we reach this region of high likelihood, of larger likelihood. Okay, and as a result, the integrated autocorrelation time, which measures the number of correlated samples in the chains between independent samples, this number is very large. Unfortunately, this is very large, as we can see here for case 2 and especially for case 6, when we use the parallel version of the Metropolis Hastings algorithm. Okay, these are the computational times. You see here that for case 6, this took almost 43 hours. These are the speed up factors compared to the theoretical speed up factors obtained from this expression that is in Q's paper. So for this for case 3 with 3 cores and with 10 cores, the real speed up factor was smaller than the theoretical one. But however, when we used the 7 cores, it was larger than the predicted theoretical speed up effect. Some conclusions: the Markov chains, they have reached the equilibrium at values very close to the exact parameters, but the statistical efficiency of these of both algorithms, they were very small. I mean, the serial and the parallel algorithms. The computational time of the inverse problem solution with MSC, it's still too large, you know, with like here taking 43 hours, which limits the number of states that we can generate with the Markov chain. So we have to reduce this computational time, and one possibility that we have already been using is to use a surrogate model, and but in order to account for the modeling errors, we can use the approximation error model developed by Jari Kaipio and his group. And we are looking forward to using actual experimental data. We hope that next month or so we'll be able to come back to the laboratory and complete the installation of the instruments to run the hydraulic circuit and obtain and actually characterize our circuit with this inverse analysis that was presented to you with simulated measurements. So this concludes my presentation. So before I finish, thank you very much, Maria Inês, Mariela, and Malena for organizing the sessions. I would like also to thank the support provided by CNPq, CAPES, and FAPERJ, which are agencies of the Brazilian government and from the Rio de Janeiro government. And also this work has been sponsored by Petrobras. Okay. So, well, thank you very much. Thank you.
Well, thank you. Thank you very much. And we have time for questions or comments.
I have one question.
Okay, go ahead.
Why do you think is it relative? Is it important the 7 processors when the theoretical speed up was less than the here? Yeah, this one. When the real speed up 7 cores, is this relevant number?
Yeah. If you the story of those cases was more or less like this. No, we have used the constant standard deviation for the proposal distribution, and we increased the number of cores. And we noticed that the largest speed up factor was with 7 cores. So that's why we have used the 7 cores for this case number 6 with a variable standard deviation for the proposal distribution. Okay. So this is a part of my answer, and the other is that this oops, I'm sorry. This theoretical speed up factor, it actually increases when the acceptance rate decreases. Okay, phi here is a transaction overhead. So if we assume that we have a constant transaction overhead, when the number when the acceptance rate is very small, is very large, you know, we may have a smaller speed up factor when we increase the number of processors. Okay? So actually this somehow passes through a maximum and decreases. Our acceptance rate here, they were very small, you know, let's see about 5%. So I guess that this number 7 ended up being the best number of cores because of the small acceptance rates that we have here.
Okay, thank you.
Thank you. So I think that this algorithm is quite good actually, but to really drop the computational time when using MCMC, we have to rely on reduced models or surrogate models. Right now we are using evolutionary neural networks as a surrogate model for this problem. It has been working very well.
Another question, or we have now, we thank again Professor